The second problem with GaN transistors, or the use of GaN transistors, the technology allows you to make tiny transistors. Their bulk resistance is very low. So in this module, this is an 8 kilowatt module. This is our Q-GaN module. There is a tiny die. It's 3 by 2 millimeters in size. And that switch is 8 kilowatts. And the issue with that is, how do you get the heat out of a tiny die, a tiny, tiny piece of silicon, where you need to get quite considerable amounts of heat? In our design, you might need to get 20 or 30 watts. In other designs, which are less thermally advanced, you might have to get 50 or 100 watts out of this tiny, tiny part. So essentially, if you want to use GaN in a new power converter design, you have a choice. You either have to have packaged parts where the die is put into the manufacturer's packaging. There are a few problems with that. One of the nice things is it's a slightly bigger package. It's not 3 by 2 millimeters. It might be 6 or 7 millimeters square, which gives you a bigger device to use. However, the thermal characteristics are not very good. They only pull heat out of one side of the die, and it's fairly limited how much heat can be pulled out. So if you used a packaged part, which is what power engineers are used to using, sort of modules or packaged transistors, you have the problem that the junction temperature will increase a great deal. You're dissipating far more power because the junction temperature increases. That reduces the total power handling capacity of your device. So essentially, I mean, in here we have an 8 kilowatt device. It can switch 8 kilowatts. In a packaged version of that, standard commercial packaged version of that, you might only be able to switch 1 kilowatt because of the thermal constraints. It will just get too hot. So, okay, option number 2, you can go for bare die. This is what we've done. Now, if you do that, you can find ways to get around the thermal issues. You can package it, and we have done so. And in here there are many exotic materials. There's a very advanced construction technology, not just for the thermal, but also for the EMC management, the RF engineering that goes into making a really fast switching transistor, where we touched upon the EMC issues before. That's all packaged in here. And that's what you have to do in order to use GaN in an efficient design, which is an efficient use of the transistors. With this kind of approach, you're going to need 8 times the size of transistors or 8 times the number of transistors. That's very commercially difficult to justify. If you go with bare die, you have a really complex piece of technology to develop. You're talking RF, microwave engineering, thermal design, mechanical design, stress analysis, in order to make a module, and this is our Q-GaN module. So what we've done is we've done all of that for you. So all of that solution is in this module, and that resolves all of the thermal issues. The thermal characteristics are so good that we are not limited in any way by the thermal performance of the module. We can handle the full 8 kilowatts from that tiny die. Any other implementation, it's just not possible. And that is fairly consistent with all GaN products out there at the moment. A lot of them are worse because they switch slower than we do, so they dissipate more power, so they have even more thermal issues. But that's a fairly consistent thing throughout the industry, that the thermal technology, the thermal design of the packaging just isn't consistent with the amount of power that you can switch. So you end up not really being able to use the full capacity of the switches, of the transistors, and that's really commercially, it's an expensive solution, so it makes it difficult to justify.